In the little world of particles, they can certainly be in two places at once. I put that in air quotes. You know what I mean by that. The probabilistic formalism can give them a chance of being at one location and a chance of being at another location. And that doesn't blow our mind because we don't directly see electrons. So if the math says the electron can be in Los Angeles and in New York City because the probability wave has non-zero value at those distant locations, that's like mind slapping. It's weird, but it doesn't cause any direct tension with everyday experience because we don't experience electrons in that pristine, isolated form in everyday life. If I was to say that, I can be at two places or that there's a probability of me being at two distinct, widely separated locations, that's far stranger macroscopic bodies. So if it's not so much of a mind crash for us to imagine electrons in this superposed state, but it is such a mind crash for larger objects, maybe it isn't true for larger objects, the suggestion goes. Maybe when things get big, the superposition principle of quantum mechanics doesn't hold. Maybe that is when things are very massive, the superposition principle does not hold. Therefore, maybe gravity, that thing that responds to mass, is intrinsically part of the way in which the measurement problem is resolved. Things are big and massive. The kind of superposition that we're used to for electrons doesn't hold. That's the idea. And again, Feynman said something like this as a possibility. Penrose has developed it. The question is, can you test this idea? And that's an interesting question, and one that, many people thought you couldn't. And look, it's difficult to test the idea in all generality. There are many flavors of an approach in which gravity can play a role in resolving the quantum measurement problem. But there is one idea that Penrose himself championed, at least in one form or another, that at least now has been tested to some degree. I think Penrose would say, well, there are variations on the theme of even that approach, and the experiments were only able to make headway on one particular approach. So it doesn't rule out the idea, because as we'll know, I don't know if we have that paper here of these underground test of gravity-related wave function collapse. Wave function collapse is this idea of going from the probabilistic haze to a definite reality. Often we talk about in terms of the collapse of the wave function. Not all probabilities that the math allows to be out there maintain their non-zero values. They collapse to zero upon some kind of interaction or measurement. So the idea here was to see, and we can keep that up and keep that paper up for a moment. The idea in this experiment was to see whether there could be an observational impact of gravity inducing this resolution to the measurement problem. And how did they do it? Well, the idea is, according to some versions, Penrose's initial version of this idea, say, if gravity is indeed what causes the wave function to disambiguate, to give one answer, not many answers, to collapse all the other possible answers, their probabilities all the way down to zero, if gravity does that, then for a large enough sample, it should be doing it to all of the particles within that sample. And it turns out that would yield a kind of spontaneous creation of energy within the object as particles sort of snap out of the quantum haze and take on definite positions. And so these researchers looked for those signatures, and they didn't find them in this particular case. And I should say, of course, obviously all experiments just set limits. You can't rule anything out usually completely, you just set limits. But the limits are such that the original proposals seem to be in tension with the data, and that's kind of cool. So it looks like a first step in the direction of trying to test some of these esoteric ideas about gravity-related disambiguation of the wave function, gravity-related solutions to the quantum measurement problem. Not a positive answer as yet, but it's nice to see these ideas being confronted with experiment nonetheless. And I believe it's the case that Penrose is developing or has developed another version of this idea in which that creation of energy would not be a part of the theory. And if that were the case, then of course the experimental results would not have any impact on that other approach. So it's not like the gravity related explanation has now been ruled out, but one version of it is in tension with the observations. Okay, so I call that kind of a fun, I mean, the quantum measurement problem is like a deep, deep problem in our most basic theory. So anything that begins to give us some experimental hint of that, I salute, and I think is well worth keeping in our list of interesting results in 2020. But certainly, the most exciting developments that I would focus upon in a year-end wrap-up are those to do with black holes, which is why our two guests of the two previous sessions were Roger Penrose and Lenny Susskind. Roger Penrose, the black hole singularity theorems, for which he just won the Nobel Prize. So that's hugely exciting. And Lenny, of course, as we discussed in our last session with him, was this and continues to be this great force in thinking about black holes, the information that falls in, how it comes out, does it come out, and if so, how does it come out? All those issues of holography and entropy and so forth. And a number of you have written questions to me, even post that live session. I want to get to some of those. So let's spend a little time on black holes. And there are some questions I've seen already in the chat, both here on YouTube, also some of the Facebook and Twitter. Let me just get to some of those. Yeah, all right. First question here. Sheila from Oklahoma asks, how did Stephen Hawking realize that black holes have entropy? That's a good question, Sheila, but I'd actually frame it a little bit differently. It's not exactly that Stephen Hawking realized that black holes have entropy. Historically, it's a little bit different, right? I mean, you know, it was John Wheeler thinking about throwing a cup of tea into a black hole, wondering where that entropy would go. It was Wheeler talking to a student, Jacob Bekenstein, or is it Bekenstein? I'm never sure about that. So I'll call it Bekenstein. Sorry if I'm saying that wrong. And Wheeler asked Bekenstein, what gives with the second law of thermodynamics? If we can use a black hole as this ultimate garbage can for entropy, we can dump all disorder in the universe into a black hole, then how do you have the second law of thermodynamics? How can you ever talk about entropy increasing if there's a garbage chute that you can sort of dump entropy out of the universe into the black hole where you'll never be able to see it again? And it was Bekenstein, not Hawking. It was Bekenstein who initially realized that when you throw a cup of tea or anything else into a black hole, you really need to continue to ascribe that entropy to the universe, because the black hole itself simply imbibes, embraces that entropy. The black hole itself can have and does have entropy. That was Bekenstein's, not Hawking, that was Bekenstein's insight. So if you don't mind, Sheila, I'm going to change the question to how did Jacob Bekenstein come to this conclusion? And we actually have I'm going to describe it in words first, give our team a moment. We do have a visual that we've been developing for another program. It's kind of a sneak peek of a program we're going to be doing in the fall. No, in the spring, I guess. We're in the fall right now. But let me describe it in words, and hopefully they can put their hands on the visual. Here's the idea. Here's what Bekenstein did. He said, look, if you got a black hole, the real interesting question is, how does the black hole respond when you dump entropy in? Now, he wasn't going to throw in a cup of tea. If this is all mathematical, of course, not like Bekenstein is going to a black hole. Let's actually, you got the visual, thank you, but let's not bring it up. Let's not bring that visual up yet. Let me explain it in words first, because I think it's too hard. But it's fantastic that you guys are able to put your hands on it. So the idea is, so Bekenstein says to himself, what if I throw a single unit of entropy into a black hole? Single unit of, how will the black hole respond? Now, how do you have a single unit of entropy? He says, well, look, imagine I have a single photon. But a single photon doesn't necessarily have one unit of disorder. You can think about, again, entropy, as we discussed previously with Lenny and with Roger. It's kind of a measure of the hidden information content. Now, if you have a photon going to a black hole, there's a lot of information in principle. Did that photon enter the top, the bottom, the left, the right? All that information about where the photon enters. So Bekenstein says, I just want a single unit of information, so I kind of want to blur out the photon so that information is not available. How do you blur out the photon? Make its wavelength roughly the size of the black hole. So kind of smear out the photon. So the only information you ever have is, does the photon make it in the black hole or doesn't it? Just one yes or no question is all that you'll be able to ask about that scenario. So Bekenstein mathematically imagines having this blurred out photon, okay, that he throws into the black hole, and mathematically he then analyzes what happens. And what he finds is the black hole gets a little bigger. That's not surprising. Black hole eats energy. Energy is like mass. The black hole's size is proportional to its mass. So if it eats a little bit of mass, it'll get a little bigger. Good. But how much bigger? And he finds that it gets bigger. Its surface area gets bigger by basically 1 Planck area. 1 Planck area. So you throw in 1 unit of entropy, and the area of the black hole goes up by 1 unit in these Planck units. And that leads him to the idea that the entropy of a black hole is accounted for by its area. Throw in 1, the area gets bigger by 1. Throw in 2, it gets bigger by 1 or by at least by 1. Now we can show that little visual. We can bring that up. So here's that smeared out photon. You see it on the left there. And if we throw that photon into the black hole, it's all smeared out. So it either gets in or it doesn't. Let's imagine it gets in. The black hole gets bigger because it just ate some energy. And now we're going to calculate visually how much bigger. So there's the area of the original black hole. Take all those tiles. These are all Planck area tiles. Let's use them to tile the slightly bigger black hole and see how they do in terms of covering it. And you see, they cover it, save for 1 little Planck area, which means that the old black hole, that's the one which at least is on my left. I never know how left and right work here. But on the left side of the image is the old black hole. The right side of the image is the new black hole. And you see the new black hole is bigger than the old one because the red tiles that perfectly covered the original black hole, they're 1 short in covering the bigger black hole. 1 unit of entropy in, area increases by 1 unit. And that's how Bekenstein comes to this idea that when you talk about black holes, the amount of entropy that they contain can be accounted for, measured by, represented by the number of these red tiles, the number of these Planck area tiles. Now you may be familiar, the actual number is usually area divided by 4 in the units where CG and H bar equal to 1 for the technical, those among you who follow this in detail. But look, if you redefine the Planck area to be Planck area as normally defined divided by 4, that's the rational way of thinking about things. Then each of those tiles has 1 Planck area. And the total entropy is just the number of tiles, which is just the area of the surface, the horizon of the black hole measured in these Planck units. So that is the answer to how Bekenstein, not Hawking, came to this idea of black hole entropy. Now, Hawking then came along, didn't believe this idea, frankly, was motivated by trying to rule it out, but he goes much further. When he tries to rule it out, he actually establishes it from a different perspective, and then comes to all sorts of other wonderful conclusions about black holes having temperature and black holes radiating and so forth. We can spend a little time talking about that. So Tanzu asks, what is inside a black hole besides the singularity? And look, in the traditional way of talking about black holes, things fall in, ultimately get crushed into the center. They don't instantaneously go to the center, the singularity. So there could be things inside a black hole en route to the singularity. But once the black hole is settled down, let's say you stop allowing things to fall into it, then yeah, what's inside the black hole is this central point, at least mathematically, where the math breaks down, the curvature goes to infinity. The curvature goes like 1 over your distance to the 6th power from that point. And the distance here is actually a temporal distance, not a spatial distance, because space and time interchange their roles when you cross over the edge of a black hole. But basically, there's nothing there except for the singularity, which is why it was so surprising when Bekenstein made this suggestion that black holes have entropy. Because normally, if you've got a box of gas and you remove all the gas, the entropy inside, now let's say it's completely empty, the entropy in the usual way that we think about statistical mechanics, thermodynamics, goes to 0. You need the gas, you need the stuff inside of the container in order for the container to have disorder. But if the black hole, think of it now like the container, if it kind of doesn't have anything inside except for this singularity, as Tanzu asks about, like what's holding on to the entropy? And that's why it was so surprising. And at least part of the reason why I think Hawking was so skeptical that this idea of black hole entropy was true. Black hole seems so thoroughly simple, right? Simplest thing you could imagine. Basically empty space with this central singularity that we don't really understand. But where could the entropy therefore be carried? That was a puzzle, and that's why it's still surprising that black holes do have these thermodynamic properties. Take another couple of questions about this. I'm particularly favoring questions that have to do with black holes. Here's another one from Neo Chrysla. I hope I'm saying that right. Neo Chrysla? I don't know. Let's see. If black holes at centers of galaxies can have billions of times the sun's mass, wouldn't they immediately crush everything around them? Well, I get the intuition, Neo Chrysla. Big is usually badder, stronger, more powerful. With black holes, the intuition is kind of reversed. The bigger the black hole, the more gentle it is in a very specific sense. I mean, you can measure that in a number of ways. For instance, think about the density of material that you'd need to have to create a black hole, right? You may recall, and this is good for, who asked for equations? That would have been spin foams. All right, spin foams, an equation. I want to actually write it down. But in the formula for black holes that initially came out of the work of Karl Schwarzschild back in 1916, remember Russian front, World War I, Schwarzschild gets Einstein's manuscripts. Often I describe it as fortuitous, strange that he got Einstein's manuscript. He was actually friends with Einstein, so it's not all that surprising that he got the manuscript. But it's more romantic to imagine he's just out there and somehow mixed into his marching orders from the military. They slipped in accidentally Einstein's paper, whatever, put that to the side. But Schwarzschild writes down the first exact solution to Einstein's equations. Einstein himself did not get the first solution to Einstein's equations. Schwarzschild did. And in that solution, he writes down the metric for what we now call the Schwarzschild metric, the metric for a spherically symmetric massive body. And the key term in that formula involves something of the form 1 minus 2gm over c squared r. The real thing is there 2gm over c squared r. Why does that matter? Well, putting all the constants to the side, that term is relevant because when r equals m, or 2gm, whatever, but put those constants aside, basically when r is equal to m, that metric has a 0 in it or an infinity depending upon which term you're looking at, and that's where the black hole edge, the black hole horizon, the notion comes from. Now that's important because R is, say, proportional to M, which tells us that the Schwarzschild radius, the radius of, say, a black hole, is proportional to its mass. Why does that matter? Well, think about the density of an object that will become a black hole. Density is mass per volume. Put mass upstairs. Now, I guess I'm speaking to spin foam and a few others who don't mind the mathematics. Put the mass on top. What about the volume? Volume goes like r cubed, 4/3 pi r cubed, say, if you're in flat Euclidean space for the volume of a sphere. But if r goes like m, then r cubed in the denominator for the volume goes like m cubed. So m over v goes like m over m cubed, which means it goes like 1 over m squared. The density goes like 1 over m squared. 1 over m squared, which means that the bigger the mass, the smaller the density, the smaller the curvature, not the bigger the curvature. So amazingly, if you have who asked that question? Neo Chrysler. So if you have a black hole that, say, has a billion times the mass of the sun, right? Those are the kinds of black holes that are at the center of galaxies. Not, Milky Way, we got a puny black hole, 4 million times the mass of the sun. But other galaxies have billions of times the mass of the sun. So take it to be a billion. If you put a billion solar masses into that formula for the density of a black hole, just work it out. I don't know the exact number, but it comes in at less than the density of water. A black hole can be formed by bringing together a billion times the mass of the sun in a volume such that the density is less than the density of water. And that will then collapse in on itself to create a black hole. And if you again take the density to be, for the black hole, its mass divided by the volume out to the event horizon, you're talking about a very low density, very small curvature. So contrary to your intuition that black holes, the bigger they are, the more monstrous they are, the more curvature they have, it's actually, in this sense, the reverse. The more gentle they are, the less dense they are, the less distortion they create to the space-time environment around them. So it's really as the black hole gets smaller and smaller that the curvature goes up and up, the temperature goes up and up. The reverse of what you would think. Harshad Kailas Pelmahale. That's quite a name. That's fantastic. What's your view on white holes? So white holes are kind of time reverse versions of black holes. Black hole, things fall in. White hole, things are continually coming out. And, people have tried to rule out these so-called naked singularities. Unsuccessfully, to date to have a mathematical proof. I don't know. I don't think we really know. Maybe we'll come upon one of these strange objects one day. They're certainly allowed by the laws of physics, just time reverse versions of black holes, but certainly no observational evidence for them to exist. So I just don't know the answer. Nobody does. Occam's razor asks, I want you to explain quantum, where is it? Sorry, Occam's razor. You were so efficient in your question. You so pared down the language, a la Occam's razor, that I don't understand the question. Want to explain, where is it? Sorry, I don't know what it is. E-Key, E-E-C-K-E-E. Could you talk about the inside of a black hole through the ER equals EPR view? Oh boy, that's a great question. How do I do that? Well, let me see. I'm going to work my way E-Key to that question. I see another one here that will help us get there. Terraformer asks, can you just give me a straight answer to whether or not something can actually fall into a black hole? A straight answer. Look, straight answers are what I strive for all the time. sometimes questions are really subtle, and having the kind of answer that you anticipate, yes or no, may be itself misleading. In some sense, whether or not an object falls into a black hole depends upon your perspective. If you are the object falling into the black hole, then you will, at least in the traditional way of thinking about black holes, you will fall in. You will make it to the event horizon, and in short order, depending on the mass of the black hole, the size of the black hole, you will find yourself increasingly uncomfortable as you get ever closer to the central singularity. You will fall in. If, however, someone is watching you at a safe distance heading toward the black hole, their perspective on what happens will be different. And this has largely to do with this weird property of black holes, which I don't know if we spent much time talking about here, but time slows down near the edge of a black hole. Time slows down. Why is that? It's sort of hard to explain, but the basic idea is that gravity doesn't just pull on matter. It doesn't just pull on energy. Gravity, in a sense, pulls on time itself, or even more precisely, gravity is the warping of time. Gravity is manifested by the fact that clocks at different distances from a gravitational source will tick off time at different rates. I think I got a visual. Can we bring up, do you have that visual about the clock? Yeah. Wow. Full service. Look at this. So you got two clocks in this little image. They're far, say, from a star, like the sun. And at this distance, if we allow their second hand to start ticking, right, you'll see that the clocks, because they are right next to each other, ticking off time at the same rate. But now, bring one clock closer and closer and closer to the star. Now, it is ticking off time more slowly. You can't see it really because there isn't enough gravity for it to make a difference. But if you take that sun and now imagine crushing it down into a black hole, that allows us no more mass, but allows us to take that clock and bring it closer to the source. And the deeper the clock goes into the gravitational well, the stronger the gravitational potential, the slower the clock will tick. Look at the second hand on the clock. That's right near the black hole there. It's ticking off time incredibly slowly compared to the second hand of the clock that's far away. Look at those two clocks ticking off time at different rates. Actually, I once wrote a short story based on this idea. I don't know if any of you have ever read this. Icarus at the Edge of Time, about a boy going to the edge of a black hole. It turned into a stage show. We're actually working on the sequel to that right now, so it'll be out at some point soon, so you can see the whole thing. But anyway, put that to the side. Why does this matter for the question that, who asked it? Terraformer wants a straight answer to whether or not something falls into a black hole. Why does this matter? Well, look, if I am far away watching you with your watch fall toward the black hole, and if I'm looking at your watch, I will see your watch tick off time slower and slower and slower, which means that your progress toward the edge of the black hole will be slower and slower and slower, which means from my perspective, I will just see you get closer and closer to the edge. But right as you get to the edge, your clock basically stops. Your progress through time, from my perspective, stops. And so from my perspective, you kind of hover at the edge. If I'm being a little bit more precise, you'll be deeply redshifted. The light that you are emitting will have its wavelength stretched out, making it ever redder in color, ever more spread out. So I will see you kind of spread out along the event horizon of the black hole, and I will never see you fall in. So again, from your perspective, you fell in. From my perspective, the outside perspective, I see you hover at the edge. So the answer is, that's the answer. It's an observer-dependent question. So, you should get in the habit. I'm not a great fan of Niels Bohr asking. I don't go that far. I think there are many interesting questions about the world that speak to our mental image about how the world works. But here's a case where taking a Niels Bohr perspective is a good one. Phrase your question in terms of an observable quantity. And so from the perspective of the observer falling in, the inside perspective, yeah, you fall in. From the perspective of the measurements, observations of an external observer, well, I don't see you fall in. And that is as far as we can go. And so that's part of the mystery. And in fact, that takes, who was it? Iki asked about the, I mean, that's part of what we need to get to the answer. What else do we need to get to the answer? Well, okay. So one of the big puzzles that Lenny Susskind, Gerard 't Hooft, many others were struggling with in this picture of black holes and entropy and information is if you throw something into the black hole from outside, right, what happens to the information that it contains? Again, if I'm carrying, the Encyclopedia Britannica or whatever, that's sort of a silly example in this modern era. If I'm carrying, a laptop chock full of interesting patterns of bits and bytes, all sorts of information, and I go into the black hole, what happens to the information that I carried across the event horizon? Is it gone? Can it come back? That was the question that people puzzled about for a very long time. Now, this animation that we just saw with time slowing down near the edge of a black hole hints at an answer. The answer is, well, from the perspective of somebody on the outside, the information doesn't really get across the event horizon. So maybe the information is stored on the edge of the black hole, and that resonates with Bekenstein's realization that entropy is measured by the area of the event horizon, because entropy, again, can be thought of as the amount of hidden information that, say, has fallen in, is no longer accessible, therefore it's hidden. Bekenstein's saying, well, it's being described by the area of the event horizon. And now perhaps we can go one step further and say it's not described only by the area, it's actually stored. That's the new idea that 't Hooft, Susskind suggests. It's stored on the surface of the black hole. And that suggests that the information can get out. Because if there's a copy of the information on the edge of the black hole, then in principle it can be retrieved. And this is the idea of holography, the holographic picture. Throw something into the black hole. Yeah, from the object's perspective, it goes inside. From the external perspective, it's on the surface. From the external perspective, you could therefore retrieve that information. It's not on the other side of the event horizon. It doesn't need to go faster than the speed of light to get out. And therefore, in principle, you can reconstruct everything that fell in from that data. That was the idea. Now, there are a lot of details that this raises, and I see a question from one person that will help us get there. Hang on, I saw it. Let me think about it. Oh, Serafina T. All right, Serafina T asks, oh, okay, I saw a NOVA program. Was it mine? Recently about quantum entanglement. No, that couldn't be mine if it was recent. I haven't done things. Oh, I know the program you're talking about. There is a program. I saw it advertised on quantum entanglement. I don't understand how entanglement doesn't travel faster than the speed of light. Right, good. Yeah, that's a good question. And that sort of will help us on our way here. So let me just say a few words about entanglement in general, and then we'll go to entanglement in a black hole. And then that will take us, if I'm not mistaken, let me just try to come up with a logical chain of events that will get us to an answer to the ER equals EPR. Yeah, I think that will get us. All right, let's talk about entanglement for half a second. And let me just talk to World Science Festival folks. In a minute, I'm going to ask if you can get your hands on that entanglement animation that we often have used with the spins, that would be useful. So what is entanglement, first of all? So entanglement is this idea in quantum mechanics that you can have widely separated particles that act as if they are right next to each other. They may start out life next to each other. You widely separate them. Now, normally when things are widely separated, you consider them to be independent. You consider them to be autonomous, right? In some sense, the very definition of autonomy emerges from spatial separation. When things are so far apart that there can't be any communication between them, between two given events. Someone articulating a sentence in New York, someone articulating a sentence in California, if they are spoken sufficiently close together in time that there couldn't have been some signal to correlate those statements, then they're independent statements. They're autonomous. They were not influenced by each other, I should say. Now, quantum mechanics offers a weird rejoinder to that, because particles, if they start out the right way, can be linked in a manner that even when they're far apart, they act as though they're next to each other. They act as though they are influencing each other. They act as though they have a deep correlation between them. And the canonical example that we often use is this notion of particle spin. Particles always spin around. Electrons have a spin known as a half. The Higgs boson has a spin 0, but let's look at particles that actually have a non-zero spin. An electron can spin. We often call it, if it's spinning from the perspective of, I'm looking at that particle right now, spinning anti-clockwise, counterclockwise, we call it spinning up. Spinning the other way, we call it spinning down. We call it spinning up and spinning down. So particles can spin up or spin down. And in quantum mechanics, you can have a weird mixture of a particle spinning up and down simultaneously. That's kind of strange, totally weird. But that's just like bread and butter quantum mechanics. So let's take that at face value. The weirdness of entanglement is that you can have two particles, and you can start them out in a correlated manner, spinning up and spinning down simultaneously. Then you can widely separate them. Now here's where it gets totally weird. They're widely separated, each doing their business up and down. Now, according to quantum mechanics, when you measure a system, you force it to anti-up and pick one outcome. So you go over to the particle, say in New York, you measure it and say it's spinning up. The other particle, California, you measure it independently and say it's spinning down. But here's the thing, if you look at both the particles at the same time, let me see if I can get in the middle of the frame here, right? You measure the one, say, on one side of the country, it spins up. The math says that the other particle, widely separated from the first, will at that very same moment snap out of the fuzzy quantum mechanical haze and spin down, even though you have done nothing to it. Entanglement influences somehow bridging the separation between particles. Do you have that visual, guys? We can bring that maybe if you do. If you don't, it's okay. Oh, good. There it is. So here are two particles spinning up and spinning down, widely separated. Let's say I go in and measure the one on the right, and I measure it, and the one on the left snaps out of the haze and spin down. That yellow line is like a line of connection, a line of quantum entanglement. And if I look away, right, allow the particles to go back to their fuzzy mixture of both spinning up and spinning down at the same time, let me go over to the other particle and measure it. I snap it out of the quantum haze, say the red one, and the blue one snaps out of the haze too, even though I didn't do anything. And again, these particles could be on opposite sides of the laboratory or the country or the universe, according to quantum mechanics. You do something to one and it affects the other. And that's, of course, why Einstein called this spooky. Spooky action at a distance. Totally, totally strange. All right, now why is that relevant? Well, what I just showed you was bread and butter, canonical quantum entanglement in an ordinary setting. My room, laboratory, empty space, whatever. It turns out that it's very interesting to apply this idea near the edge of a black hole. And that's really what Stephen Hawking did. What Hawking found in trying to disprove Bekenstein's idea that black holes have entropy, what Hawking found is that when you include quantum effects near the event horizon of a black hole, something weird happens. So in quantum mechanics, particles can erupt out of the vacuum. Particle-antiparticle pair can erupt out of the vacuum. They exist for a moment, then they hit each other, and they quickly annihilate. But that kind of process, quantum agitation in the very fabric of empty space itself, this is something that happens everywhere. Now, what Hawking found is near the edge of a black hole, something curious can happen, because when this particle-antiparticle pair forms, sometimes one member of the pair can get sucked into the black hole. The other member's outside. It doesn't have a partner with which to annihilate any longer, and it just rushes out into space. So let's see if we can. Do we have that? I think we do have that kind of visual, don't we? Yeah, good. So the red and the blue particles here, particle-antiparticle pairs, and you see the red ones are rushing away, the blue ones are falling in. The particles can't re-annihilate and go back into empty space. So this is this idea of Hawking radiation, those red particles, Hawking radiation. Quantum particle fulminations, particle-antiparticle pair created, particles or antiparticle, whatever falls in, the particles rush away and go out. Now, that's the situation, ignoring quantum entanglement. But when a particle-antiparticle pair forms, they're actually entangled, just like the red and the blue particles I showed you a moment ago. So the real picture of what's going on, if we can bring that up, is when the particle-antiparticle pair form, they have a thread of quantum entanglement connecting them to each other. And in fact, that's just one pair. Do we have one with multiple pairs for? Yeah, good. Here we go. Here's with multiple pairs. Now look at what's happening here. You've got this tremendous amount of entanglement, quantum entanglement, stretching right across the event horizon of the black hole. And so an interesting question is, how does the event horizon of the black hole affect those threads of quantum entanglement? That is a deep and interesting question that people have struggled with for some time. And you can actually keep that picture up. I like that picture, if you will. And the question is, for instance, could it be the case that the edge, the event horizon of a black hole, maybe it snaps those threads of quantum entanglement? Now, if that were the case, you can imagine like a tense thread. When you snap it, energy is produced. And if that were the case, then there'd be energy being produced at the edge of the black hole. This is what gives rise to, you may have heard of this idea of firewalls, this possibility that has been floated that the edge of a black hole might actually be a firewall. Because if those threads of quantum entanglement were snapped, the energy there would be create a very hot environment that would be like there being a firewall at that location. Now, why would the threads be cut? Well, from a general relativity standpoint, they shouldn't be cut, because the event horizon of a black hole isn't something in the general theory of relativity that you can touch or smell or hold. It's a location of no return, but it's not signposted in any way. There's nothing unusual happening at that region of space from any local perspective. I'm fond of saying Earth itself could have fallen over the edge of a black hole according to the general theory of relativity. We could have fallen over it just now, and we wouldn't notice anything, because the space that we call the event horizon is not a tangible thing, at least in the usual formulation of the general theory of relativity. But this perspective would suggest that it might be. But again, if you come at things from a purely general relativity point of view, you say those lines of quantum entanglement will not be cut. They simply extend right across the event horizon. So why would one think they might be cut? Well, here's the thing. Those red particles on the right-hand side of that image, the Hawking radiation, for that radiation to carry the information content of everything that fell in to form the black hole, that radiation needs itself to be entangled with other radiation that has come out of the black hole. If all that radiation, they're completely independent, not entangled with each other, then there's no information content. Information comes from the entangled interrelationships between the radiation, the photons, the particles that are coming out. But there's a theorem that says that I'll say it loosely, there's a precise version of it. The radiation particles can't both be entangled among themselves and with the blue particles inside. You can't have that kind of threesome when it comes to entanglement. Collections, say 2 collections of radiation particles and the blue particles, those are 3 collections of particles. They can't be all mutually entangled. This is this idea that you may have heard colorfully, maybe sillily, if that's a word, ridiculously, perhaps better, described as the monogamy of quantum entanglement. You can't have a threesome. And if that's the case, if you believe that the information does come out of the black hole, as Gerard 't Hooft and Lenny Susskind have argued, if that information content gets stored on the outside and can be retrieved and indeed would come out with the radiation, if you believe that is the case, then you're in a bit of a pickle, because you need the red particles to be entangled among themselves, and you also need them to be entangled with the blue. Something's got to give. You can't have all that entanglement. Too much entanglement. What do you do? And so that's why some have suggested that the entanglement with the blue particles gets cut, and that's where this firewall idea initially came from. There are other solutions that have more recently been described. Maybe I'll get to them in a moment, but I think that's enough to kind of give a little bit of motivation to Xy's question. Actually, you probably didn't know you were going to ask a question that was going to take this long for me to answer. But, to get to the answer to your question of Einstein, Podolsky, Rosen, and Einstein, Rosen, we need kind of this background. So let me see if I can get there. So let me. There are 3 things that I want to say to get there. Number 1 is, Einstein, Podolsky, Rosen. I think we have that paper somewhere in our list of visuals. Can we bring that up? I don't know if you can do that. Is that it? I don't have my glasses on. Yeah, there it is, 1935. So this is the 1935 paper of Einstein, Podolsky, and Rosen. This is the paper in which quantum entanglement wasn't really discovered. Schrodinger knew about quantum entanglement, but this is a place where quantum entanglement was brought to the uncomfortable attention of the quantum mechanics community, because Einstein said, how could it be that you could have these widely separated particles? And I realized I didn't fully answer, whose question was it? Yeah, Serafina, right? So Serafina T asked, how can you have these widely separated particles communicating and it doesn't break the speed of light barrier? So let me just quickly answer. The answer to that question is, these 2 widely separated particles, their behaviors are correlated, but we do not believe that one is sending information to the other. It's not saying I came out down, you got to come out up. Rather, at each widely separated location where you do this experiment of measuring the particle spin over and over and over again, you just have a random list of results in New York: up, up, down, down, up, whatever. In California, you'd have another random list of results from measuring the other particle: down, down, up, down, down, and so forth. No interesting information in any of that data. The only interesting information comes when you bring the 2 data sets together and compare them. Down, up, down, up, down, up, down. You get perfect correlation between them. But in order to do that comparison, you need the slower than light communication channel. You got to bring them together. You can't do that comparison using quantum entanglement. You got to do it with the ordinary means of comparing the results. And so the weirdness, the beauty, the insights of quantum entanglement can only be extracted by a slower than light comparison. And that's how quantum entanglement squeaks by the dictum from special relativity that nothing goes faster than the speed of light. Good, all right, I've closed that loop. Now let's go on then. So we had the EPR paper. Let me bring that back up. That's where this entanglement idea really was brought to the fore, 1935. This other paper by Einstein and Rosen, same year, right? Can you make it a little bit bigger? Yeah, thanks. Because I don't have any glasses here. I can't even see it. But yeah, this is a paper. What does it say? That says July of 35. I can't even see. But this is another No, received May of 35. I see. So this is another paper of Einstein's, seemingly completely disconnected from the EPR paper on quantum entanglement. This is a paper in which Einstein and Rosen introduced this idea of wormholes, that you can have, tunnels through the fabric of space connecting widely separated regions. And there was no suspicion whatsoever that these papers had anything to do with each other. And what Ecke asked about was the recent work. And this is work due to people like Susskind, who we spoke to recently, Juan Maldacena, many, many others who deserve credit for developing these ideas. That the idea that these two papers are actually profoundly connected to each other. What's the rough idea? And then get to a visual if I can bring it up. And guys, just, I want to bring up the black hole, wormhole, entanglement thing. But what's the basic idea? Look, if you got two widely separated particles, okay? One way that you can imagine that they're secretly connected, right, is if there's a wormhole from one to the other. And if there's a wormhole, that's a shortcut that kind of brings the particles together, even though in the real space that we see around us, they look like they're widely separated. That has the ring of relevance to entanglement. Entanglement is widely separated particles that act like they're next to each other. If there's a wormhole, maybe they're acting like they're next to each other because they secretly are next to each other through the shortcut, through the wormhole. That's the basic idea. Now, to explain that a little bit further, there's one more insight that I should give you. This is this ADS-CFT insight that you may have heard something about. Yeah, actually, Lenny and I spoke about it a little bit. This is this ADS-CFT insight that you may have heard something about. Yeah, actually, Lenny and I spoke about it a little bit. This is this talking about these ideas without a concrete realization of these ideas. They weren't as fully embraced as they were post Juan Maldacena's breakthrough. What is that breakthrough? He showed that in certain environments, anti-de Sitter space is the name, but the details don't really matter. In certain environments, if you have physics in some region of space, he showed using string theoretic ideas that that is absolutely equivalent to a dual description that only refers to the boundary of that region. And in fact, a gravitational theory in the so-called bulk, the volume of space, is exactly equivalent, according to these ideas, to a non-gravitational theory on the boundary of that region. And that's where the notion of hologram really comes in, right? Boundary of the region, fully equivalent to the 3D stuff that's happening in the bulk. You have a hologram, 2D piece of plastic, you illuminate it the correct way, it creates a 3D image. So that 3D image is actually equivalent to the two-dimensional piece of plastic. Here, the 3D physics would be totally equivalent to, say, the 2D physics on the boundary. Now, people then took this further, Juan, Mark von Ramsdorff, many others, and noted the following. I'll describe it in words, and then I'll see if I can bring up the visual. So the word description is this. If you take two black holes, imagine, black hole here, right? Each of them has a dual description in terms of a quantum mechanical theory on the boundary. If you then entangle those quantum mechanical theories, connect them with those yellow lines of quantum entanglement, it turns out that that's precisely equivalent to connecting the two black holes by, you guessed it, a wormhole. So a wormhole connecting the two black holes, that's the ER, Einstein-Rosen bridge, the wormhole, is equivalent to the EPR, entanglement connection between the two boundary theories, the two boundary descriptions. And I think we can we bring up a visual? Yeah, you guys are amazing. Thank you. All right, so here's a black hole, a visual of a black hole. And again, this black hole is equivalent to a theory on the boundary, which I'm going to draw in red here. It's actually a thermal theory. It's a hot quantum mechanical theory, so making it red, there's a lot of sense in that. Imagine now we got two black holes, each described by this thermal quantum mechanical theory in the boundary. If we entangle those two quantum mechanical theories, there are these yellow lines of quantum entanglement. That's equivalent to joining the two black holes by an Einstein-Rosen bridge, a wormhole. So, Eki, if I'm saying your name correctly, I'm sorry if I'm not, there is the answer to your question. You've got the EPR, the yellow lines of quantum entanglement, and you got the ER, the Einstein-Rosen bridge, the wormhole, connecting the two black holes. And so these two 1935 papers of Einstein that at that time seemed completely separate, disconnected, they are deeply connected according to these ideas, as we just saw. That's the basic idea. Oh, hold this. You can hold that visual for a moment. Don't go any further on this. We're really showing our full hand. As again, this is actually a sneak peek. If you can hold that without going any further on the visual, I'd appreciate it. Or if you go all the way, whatever. So this is a sneak peek of a program that we're doing, World Science Festival. What you're seeing right there, what you just saw, is if you then cut the lines of quantum entanglement, you can ask yourself, if you break the entanglement in the quantum mechanical boundary theory, what does that do in the interior? And the answer you can see in this image right here. The interior kind of becomes pixelated. It gets pulled apart. So the fabric of space gets cut up into individual chunks that are no longer connected to each other. So the idea, and this is work developed by Mark von Raamsdonck, others as well. The idea then is that the threads of quantum entanglement may themselves be interpretable as the threads that stitch together the very fabric of space in the interior. And without the threads of quantum entanglement in the boundary quantum mechanical theory, the geometry of the bulk theory balkanizes, falls apart into individual chunks of space that are no longer stitched together into the smooth space-time fabric that we are used to. So that's the idea that it's in its infancy, but this idea that space-time itself may not be fundamental. Space-time itself may be built up from these more fine ingredients, the little blue dots, little pixels that you see in that image. And how do they get stitched together into the smooth fabric of space-time that we all experience? The answer is they may get stitched together. They may get stitched together by the threads of quantum entanglement. That is a fantastically beautiful idea. One of the most beautiful ideas that I've seen in recent discoveries in physics. Very much a work in progress. But if you were to ask me to look forward and think about where physics is going in the not too distant future, I would say that that is a likely contender, that we will have descriptions of physics in which space and time, as we usually describe them, as the smooth continuum in the Einsteinian approach, that space-time itself may emerge from a more fundamental starting point. And that fundamental starting point will involve some kind of ingredients like those little blue dots. And only when those little blue dots are stitched together by the threads of quantum entanglement in the correct pattern, in the correct way, will space and time, as Einstein thought about them, will space and time emerge. That's the beautiful idea. Well, I guess we kind of answered Eki's question. ER equals EPR. I hope that did it. I don't even know if Eki stuck around, or EC, or whatever it is. Stuck around for the answer, but I hope that was pretty clear how all those parts fit together. I saw another question roll by. Who was it? I don't know if I can find it. Once things roll by, I can never find it. Well, I don't know who asked it, but there was a question. Someone asked, "What is the page curve?" I can try to answer that if anyone's interested in that. Anyone want to hear a little bit about the page curve? There's always a little bit of a time delay, so I don't even know if. And so maybe I don't know. I'm going to assume that someone's going to say yes to the page curve. There we go. Many people saying yes. Thank you. How could you say no to the page curve? Well, so Don Page is a brilliant physicist who's been thinking about black holes for decades. And he noted in a manner, well, let me use the visual imagery that we've already developed. So remember I had that visual not too long ago where I had, all the Hawking radiation, the red particles on the outside of the black hole, all quantum entangled with the blue particles that are inside the black hole. In some sense, what Page noted was you just can't have that much quantum entanglement. What he really noted was that when you appropriately define entanglement, there's a kind of entropy associated with it. Entanglement entropy is usually called. And it's a measure, in some sense, of the amount of entanglement. And what Page was noting, especially if you believe that all the information comes out of a black hole, in the language that he was using, he was noting that at the beginning, before the black hole has emitted any Hawking radiation, there's not going to be any entanglement entropy because there's no radiation on the outside for the black hole to be entangled with. Good. Toward the very end of the black hole's life, when it's really small, and as say the black hole disappears even, let's say it's all turned into radiation, Hawking radiation, again, there can't be at that point any entanglement entropy because it's now the reverse. It's all radiation, no black hole. So how can they be entangled? So it starts out with no entanglement entropy, all black hole. It ends with no entanglement entropy, all radiation, which means that somehow, as the entanglement entropy grows, there has to come a point where it turns around and comes back down. And it's been a real puzzle for people to fully understand how that entanglement entropy follows that curve. And what's happened very recently, and we don't have any visual on this, we haven't developed any yet, I don't think. What's happened very recently is there have been new calculations undertaken that have provided a means of calculating the entanglement entropy in basically a completely geometrical way. And people have found that when you do it correctly, it's as if there is a surface within the black hole itself that forms at late times after the black hole has been around for a while. And that surface, in some sense, captures the entropy of the particles inside and sequesters them from the entropy count. And that's what brings down the entanglement entropy between the external radiation and the internal radiation. And that has finally allowed physicists to calculate from first principles this Page curve. Entanglement entropy goes up and goes down in a manner that agrees with the expectation that it will have that shape. Now, the beautiful thing, to some disturbing, but I think to most people pretty wondrous and gratifying, is that many people thought that we would need quantum gravity to be able to calculate this Page. We're talking about entanglement, any quantum gravity was the thought was. But in reality, you don't. General relativity itself is so smart. Gravity is so insightful on its own that these calculations, pure geometry, purely geometrical calculations, are able to get the curve. So in some sense, this has led some people, and we had discussed this in the conversation with Lenny Susskind a little bit, to think that, maybe general relativity kind of knows things about quantum mechanics already. And maybe that's why the traditional approaches to quantizing gravity have failed, because unlike electricity and magnetism and the weak nuclear force and the strong nuclear force, which have a classical description, which you then quantize, and then it agrees in that quantum mechanical formulation with observations, gravity, maybe it isn't a theory that you start classically and then you quantize. Maybe general relativity, even the classical theory, is not so classical after all. Maybe it sort of has aspects of quantum mechanics somehow woven into its basic structure, and therefore to apply the traditional quantization schemes to gravity won't work, because gravity is not like the other forces. It already has some quantum inside of it. So in some sense, maybe gravity and quantum mechanics are really deeply linked. Kind of takes us back to what we discussed at the outset, this gravitational induced collapse of the wave function. I'm not saying that they're the same by any means, but this notion that general relativity and quantum mechanics are kind of linked together profoundly. That's probably a correct idea. And I'd say that's certainly going to be one of these ideas going forward. There's another animation that I know that we have somewhere. It's kind of fun. We just made it for this other program. Can you get that wormhole octopus like, not animation, but that, I think it's a still image that we have. Yeah, it's kind of beautiful. And this kind of illustrates this notion of the entropy of the particles inside the black hole somehow being incorrectly described when we think about it as independent contribution to entropy, independent contribution to these entropy calculations, because the notion would be through wormholes, these particles on the inside are directly connected to the outside. They're not as inside as you might have thought, and therefore dividing up their contribution and thinking of it as being an inner part is wrong. And thinking about the inside being entangled with the outside would be, in some sense, an overcount, because the inside and the outside, in some sense, would be identified, would be the same through these wormhole connections that you see. The wormholes are these kind of tube-like shapes that are going from the inside of the black hole to the external space. So this is another version of that same idea, suggesting that the inside and the outside are not as logically separate as you might have thought. So that is certainly a very provocative idea that will continue to be developed as time goes by. And again, I would consider this picture to be, again, among the images that you should have in mind when you think back on 2020, right? These are the ideas that were developed before the end of this year and will have a great impact going forward. All right, see if there are some other questions that I might turn to. So Gideon Omeda asks, my question is, since molecules act like waves in the double slit experiment, shouldn't the interaction between the particles within the molecules collapse their wave functions? And yeah, it certainly can be the case. The self-interaction of particles, if they are of the right sort, can certainly play the role of an observation. An observation need not be external. It can be internal in the sense that some particles within a structure can act as the disambiguating interaction on other particles. So yeah, you got to be real careful. If you try to do the double slit experiment with larger collections of ingredients, you have to be careful about those kinds of interactions. But people have successfully done double slit experiment with larger structures. Usually they are a crystalline structure where it can really be thought of as an aggregate as opposed to itself being a composite. If it's a sufficiently stable and rigid molecular form, you can act as though it is a particle in the double slit experiment. And indeed, they have successfully carried out these kinds of double slit experiments with larger molecules. But fundamentally speaking, yeah, you're absolutely right. What else do we have? If there is no... So Raghav Anand, if there's no time inside a black hole, how does its singularity exist? I wasn't saying that there's no time inside a black hole. Sorry if I made it sound that way. What I was saying is that the roles of space and time interchange when an observer falls over the edge of a black hole. So normally you think about a radial direction going from outside the black hole, hits the event horizon, and keeps on going to the center. That radial direction, once you cross over the event horizon, has a different character than you might have thought. The radial direction really becomes a temporal direction. And that actually offers deep insight, because you might ask, like, why is it actually impossible for something to escape once it falls over the edge of a black hole? Again, Hawking radiation isn't really escaping the black hole, created at the edge and then it's flying away. Something that falls over the edge, how can it be argued that it cannot escape? Well, once you think about the radial direction as the temporal direction, now once the object crosses the event horizon, its motion toward the singularity is through time. So for it to come back out, it would have to reverse its motion through time. We're not too surprised by the inability of objects to not be able to reverse their motion through time. That's not surprising based on our understanding of how the world works. And so there is time inside the black hole, and it helps us explain why something inevitably goes forward, because going forward is going to the future. And just as you can't prevent yourself from going from one moment to the next, neither can any entity that falls over the edge of a black hole prevent itself from going ever closer to the singularity, because that is going from one moment to the next, as understood within the space-time geometry within the event horizon of a black hole. Okay, what else here? That's kind of a good amount of ground that we have covered. Let me see if there are any other good questions. At some point I gotta go inside and get cleaned up and ready for our big New Year's party. Not going anywhere, and I hope you aren't either. Those of you who, maybe some of you, have any of you actually spent the New Year's moment with us? If you are, just note it in the chat. I'd be deeply honored, and sorry that I didn't note that it was 12 midnight in your time zone. But yeah, I hope no one is going to go out. Please don't go out. Let's just beat this virus. Do everything we can to prevent it from spreading further. So, but no, I can do a little bit more before my energy just is used up. All right. Someone's asking repeatedly, Dinesh Reddy, is time continuous or discrete? That is not suggesting that if you too have 1,000 question marks in your question that I will address it, but it did catch my eye, Dinesh. Is time continuous or discrete? I wish I could give a real snappy answer. I don't know. So obviously in the general theory of relativity, Einstein used the same kind of time that Newton was using, the same kind of time that we intuitively use, which is this continuous notion of time. Now, once quantum mechanics gets into the story, we're used to the fact that things that are continuous often do become discrete. Energy
Hello, today we're going to look at Planck units. When we measure things, we use three very basic measure types. We think of mass, which in SI units is measured in kilograms, and we think of length, which in SI units is measured in meters, and we think of time, which in SI units is measured in seconds. Now, the important thing about mass, length and time is that the kilogram, the meter and the second have nothing special about them. Sometime in history, somebody decided that a certain mass of material was deemed to weigh a kilogram. And somebody decided that a certain length, maybe the length of a man's arm, was defined as being a meter. And somebody defined some sort of unit of time on a clock as equaling 1 second. These units were simply historically derived. Somebody decided that that particular unit fitted the mass or the length or the time. And the question we're going to ask today is there any fundamental measure of these units that doesn't require some kind of historical perspective, something that humans have done in the past? Well, if there is, we need to relate it to things that are constant throughout the universe. What do we know that is constant throughout the universe? Well, we think we know three fundamental constants. That is the gravitational constant, Planck's constant, which is Planck's reduced constant, that equals h over 2 pi, and c, the speed of light. What are the known values for these constants? Well, g is 6.6 times 10 to the minus 11 Newton meter squared kilogram to the minus 2. H bar is very approximately 10 to the minus 34 joule seconds. And c is about 3 times 10 to the 8th meters per second. But of course these three
whatever. It turns out that it's very interesting to apply this idea near the edge of a black hole. And that's really what Stephen Hawking did. What Hawking found, when you include quantum effects near the event horizon of a black hole, something weird happens. So in quantum mechanics, particles can erupt out of the vacuum. Particle-antiparticle pair can erupt out of the vacuum. They exist for a moment, then they hit each other, and they quickly annihilate. But that kind of process,
Yo, shit,
quantum agitation,
was I really not fucking...
something weird happened. So in quantum,
No way, I wasn't even voice recording any of that.